So sustainability, designing with sustainability in mind, that has a lot to do with life cycle costing and life cycle assessment. And I should, supplementary to what Dale just said, I've been working with COWI for the past 23 years, it's many years. My background is chemical engineering, and through those years I've been working with service life, corrosion and cathodic protection, and I'm also a NACE cathodic protection certified specialist.
Okay.
I think it's the first one, which is very dark maybe. So first introducing sustainability, a little on background within COWI, life cycle cost and life cycle assessments, different words on that. But sustainability, that includes a lot of different topics, environmental sustainability, reducing the energy consumption and carbon footprinting. Economy, we all know that this has a very high influence on decisions being made. And it is also including social sustainability, which I will not say many words about in relation to our presentation today. But I could say, I mean, on some of when we do specifications for the Danish road authorities, they also have requirements that all the materials that goes onto a construction site may not be produced by children anywhere in the world, for instance. And we do have colleagues in our environmental department that actually follows up on that does not take place. I thought I had moved these animations. Well, defining sustainability in the Brundtland Commission that took place some years back is developments that meet the needs of the present without compromising the ability of future generations to meet their own needs. That's a very broad term, and you have to try and define it even in more details followed from that. So it's minimizing harmful impacts on the environment, and very often it's trying to optimize what you're doing. So it will not be in order to meet this broad definition. So what we're talking about is in design works. Very often, as I write down here, durability is somehow included in life cycle costing or the economic sides of things, because we normally have a surface life requirements, at least for the very large civil structures. And included that is durability requirements. So very often in designing we are focusing on this area in combination with the durability. But in future, probably to a high extent, we'll have to incorporate some of the other components as well in our designs. This is basically showing that you have different phases of a project: pre-design, conceptual, detailed design, and it's always going in and that out of that. And here the paradox in decision making, that at a later stage in your design process you make decisions, the higher the impacts and the consequences might be, with, especially if you make late changes. I think we all know those from different projects. A little on why we've been dealing with this within COWI. We had our Danish cement producer. We have one cement producer in Denmark. They said, "Oh, COWI are doing work on climate strategies, so we'd like to talk to you about how we can deal with these things, also in relation to environment." We have legislation on it will cost them money the more CO2 they emit to the surroundings. So they talk about a license to operate. They would like to focus to a higher extent on applications and optimizing things, on how are things used in real life. And within all of this, you have to recall that cement throughout the world is responsible for 5% of the CO2 emitted. 5%. So our industry with large civil structures and buildings and so on has a very high impact on the environment. Followed from that, we thought this is obvious. We need to define a strategy within our COWI group on how to deal with these things. And they've had a very big interest throughout our company doing so. We also have in-house now a certified cradle-to-cradle certified employee. And what we thought was we had to define what are the things that we could actually service in this relation. And it may sound very simple, but coming from a civil engineering business units, and you have all the environmental groups from all. One of our big challenges was to learn to speak the same language across these units. An environmental person does not necessarily know that cement and concrete is not the same thing. It might say it's a simple thing, but it's of course very important. We defined also that our mission or objective in COWI, of course, we're not salesmen. We have no ambitions of selling more cement or replacing glass or woods or anything with cement. Or we just want to be consultants, and that is providing the basis for decisions made by others, so that you have all the information lined up in order to being able to make the right decision on that. And speak up if you have any questions, or yeah, please. Of course, we like to be part of developments, and we also want to be able to participate in making structures greener. That is very much an optimization project. I mean, if we compare to a reference basis, can make the same structure as durable with another mixed design, for instance, why not do so? And as consultants, we're not a university, but we like to apply science. the ETSI project, I'll get back to that, is an excellent opportunity for us for doing so. We know that there are challenges with premature deterioration, and very often it could be low initial quality and lack of maintenance. I'm sure the design was not getting this result when you strip the formwork, but things like this, and of course very often not to quite the extent as that, makes of course the service life lower than what you expected. When we do strategies for total service life, this is an example I'll give you on how to apply successive calculation methods in doing so. That is not always used, but as a minimum we will list up, and Carola will get back to this in detail, listing the critical and limited parameters for structural design and durability, and then set forward a number of strategies that can meet these durability parameters. What we then do in relation to life cycle cost is that we price all of the components that goes into this strategy, also including variations and uncertainties, and also throughout the service life looking at what are the operation maintenance costs during the service life, repair and replacements, if any. Also indirect costs, for instance, if you plan on or have a strategy where you have to hold up traffic at some stage, that is also a cost for society. Holding people, preventing them from getting to work, for instance. Then we would carry out a sensitivity analysis. One of the highest impacts is on interest rate. That has a very high impact on what decision you make based on these things. And that should all lead to that you have a part of selecting the optimum strategy for your design. Carola will get back to details on this. If you follow codes and standards, maybe you don't exceed service life on 50 or 70 years, but if you want to have a very long service life, you have to think about different strategies. Oh, that was a bit too fast. Successive calculation method is basically where you make your best estimate of minimum, maximum, and likely pricing on different construction items. And it's a tool then based on how good you think you are at guessing these things, you'll get an expected average value. Also the variance is the same thing that you can calculate. It's calculated based on your input parameters. And following all of this, I'll give you an example on pricing life cycle costs on this. This is based on actual results, different designs for marine environments in the Arabian Gulf. So that could also be on a very aggressive environment here in the States. Required service life 100 years, and of course the structure should be kept safe. A minimum on repair works and some requirements to codes to be used. Long list of different strategies. Again, this is a picture I took many years back on one of our bridge columns on our motorways. I'm sure they did not design using only 8 millimeters of cover on that one. Setting forward different strategies. One could be a carbon steel reinforcement with an 80 millimeter cover. Designing with crack width on 0.1 millimeters. I think that's about 3 mil in the US, if I'm not too mistaken, around that. Very strict requirement. And then after 35 years, using a cathodic protection system to reach 100 years of service life. Strategy, and that could be a system like this, a preventive cathodic protection system. And when I look at this, there's a picture taken from the Øresund Bridge, which was built some years, now it's nearly 10 years. I look at it and think, where's the concrete going to go? But we've seen the concrete structures now, but that is a challenge. I mean, all the aggregates, how to get that inside of this, but that's another challenge. So it's outside this. Also a strategy on using different stainless steel reinforcement, different grades, up to, I think you call it A4, up to a duplex steel. Smaller nominal cover because you don't have a corrosion issue, and the design can then be made with design crack width on 0.025 because you don't have a corrosion issue when it's stainless steel. And last but not the least, a strategy saying, okay, what if we have a relaxed crack width and we use cathodic prevention from day one? So those are the 3 scenarios. And it could be like this, where you have anode ribbons, a titanium conductor bar, and then of course your reinforcement. Calculating the quantities that you'd use, I mean, the importance of the crack width makes that you need nearly double the amount of carbon steel with a very strict crack width compared to the other. And as you can see, the stainless steel solution is not entirely stainless steel, it's a selective use, so you only use the stainless steel where it's needed the most. That means the tile and the splash zone.
But then don't you create a more corrosion problem when you have different materials?
No, not if you combine carbon steel and stainless steel, you are fine as long as the carbon steel is still in the passive area. So you need to have the zoning up. Stainless steel is a very poor cathode, so that's another issue that makes it not that bad. But you need to know what you're designing. You need to know that the carbon steel is placed outside of risk area.
Okay, I missed the last picture. Can you go with a picture of an anode?
Yeah. We'll have a presentation on cathodic protection later. You have the reinforcement bar here. And underneath, you can see there's an anode placed here. That's the ribbon. So that's a mixed metal oxide titanium coated ribbon. And then you have a current feeder. That means where current are introduced to your structure, and it will then distribute along those. We'll get back to the principles on how this works when we have the cathodic protection presentation later. Different variations. We had actual prices on all of these different issues. Also on installing cathodic protection, also replacements, repair works, etc. And then in relation to sensitivity analysis, we said 0%, of course that's going as low as possible, and up to 7%, I think we don't normally see higher interest rates specified. But 7% is what the Danish road authorities request us to use in updating in relation to repair areas. It's a very high percentage, but I have a feeling that it might reflect that they don't have that many money to spend, and using a high interest rate would then postpone your investments. And something in between. If we then look at 0% net interest rate, accumulated life cycle costs, we then have the stainless steel solution. It's all other equal. We don't expect any repair works during the entire service life of this.